This lesson is a review of functions, relations, domain, and range. This was covered at the end of last year, and the focus is ensuring that you have a decent understanding of being able to differentiate between relations and functions and being able to determine domain and range. We'll start with a really quick breakdown of interval notation. Interval notation is just an easy way to look at the range of numbers in a set. So an easy example is if we look at a number line, here's our number line, and we've got -5, 3, obviously 0 is here in the middle somewhere. If we've got a point which is inclusive between -5 and inclusive at 3, then what that really means is we're including -5 and including 3 and every single value in between it. To write this in interval notation, and just to point out, remember the colored in circle means inclusive, which means that the 3 is included, and it also means that the -5 is included. When we're looking at using interval notation, then if it is inclusive, then the lower bound will be represented by a square bracket, and the upper bound will also be represented by a square bracket. Okay, so if I was going to write this using interval notation, I would be saying that x is an element, so that's our set notation, inclusive between -5 and 3. All right, if it is non-inclusive, so non-inclusive means that it doesn't include the value. So if we're talking about the same scenario, let's put it in green. We've got -5 with an open circle up to 3 with an open circle. And the open circle means non-inclusive. It basically means that the -5 is not included in the set. And here it's also saying that the 3 is not included. Then our lower bound will be a circle bracket, and the upper bound will also be a circle bracket. So we would say here that x is an element of -5 through to 3, non-inclusive, with -5 and 3. Okay, so that's basically it. We just have to make sure that whatever the variable is, we're stating that at the start, is an element of, and then we're using either our square brackets or our circle brackets, depending on whether it's inclusive or not. I should also say that there is other symbols that say the same thing. We could also write this as -5 is less than or equal to x is less than or equal to 3. The inclusive, the equals, is part of this statement, whereas in the non-inclusive, we would have -5 is less than x is less than 3. There is no equals there. So when we're talking about inclusive, we're talking about less than or equals, and when we're talking about non-inclusive, we're talking about just a less than or greater than sign. Okay, so we're going to do a couple of examples here. They should be nice and quick. So for A. Now, note this here. This arrow means that it's going to continue there forever. So it's going down to -infinity. Now, just to make sure you understand, we cannot be equal to -infinity, but we can be approaching it. So that's going to be non-inclusive. Our variable is x, and we're at 2. It's non-inclusive, so it doesn't include 2. Open circle. So to write this, we would be saying that x is an element between -infinity through to 2. Both are non-inclusive. We could also write that as x is less than 2, because that would be true for all as well. So that's an or. You don't have to do both. In this case, we're just focused on the interval notation. All right, so here we have a lower bound of -3 and an upper bound of 5. -3 is inclusive, see it's colored in, and 5 is non-inclusive, it's not colored in. It's an open circle. So here we are saying that x is an element between and including -3, but not including 5. So square bracket for -3, circle bracket for 5. And then we've got 2 here, so there's going to be an or. So the first one is between 1 and 3. So x is an element inclusive of 1 to 3, but not including. or, so that's our set notation again. So it's a union. Lower limit is 5. And because we've got that arrow going off forever, we're looking at positive infinity. So positive infinity, and we can't be equal to that. All right. So that's a little bit of a review on interval notation. That will be something that we keep on coming back to over and over again. So it's important to understand that notation and not find that difficult. Okay. The second thing to review is relation and functions. We'll start with relations because all functions are relations. A relation is basically a set of ordered pairs. Basically, that just means it's got coordinates. So, for example, we could say it's a set. So remember our set brackets. And we've got 0.00, 1, 1, 2, 2, and 3, 3. So the fact that we can sketch that, and we've got our points, 0, 0, 1, 1, 2, 2, 3, 3, and we've got our coordinates there, then it's definitely a relation. We could also look at something like x squared plus y squared is equal to 1. So this one's a little bit more complex. It's also a relation because for a set of possible x values, we could work out the y value. We could get an ordered pair. So for example, if I let x equal 1, then what we end up with is we've got 1 squared plus y squared is equal to 1. When we rearrange that, we end up with y squared is equal to 0, and therefore y is equal to 0. So here we've got an ordered pair, which is 1, 0. Now we can do that with a number of different values, but let's say we put in 1, we put in -1, we get -1, 0. We put in 0 and we get 1, or we also get -1. Now, I'm not too worried about the process there. This will be something we work on when we start looking at different types of functions. But being able to determine this set of ordered pairs here also suggests that that's a relation. And our relation, in this case, allows us to sketch a circle. So basically, any type of two-variable equation, any set of coordinates, we could just do something like y equals 2x plus 3. Now, we all know we can graph that. Again, that would be a type of relation. And this particular relation, we know it's got a y-intercept at 3. And then we can work out some extra values. So this is 3, this is 1, 5, and so on. So we could sub in 0 and we get 3. We could sub in 1 and we get 5. And we could get as many ordered pairs as we like to create that function, to create that relation. Now, if a relation is a set of ordered pairs and a function is basically a special relation where there is only one y value for every x value, that means when we look at a function, we can't have 2 points on top of each other. So as long as whatever we're sketching doesn't have 2 points on top of each other, then it's going to be a function. An example of something that is not a function would be something like an inverse parabola. So we've all seen these. For a selection of x values, there are 2 y values. And as soon as that happens, as soon as we get 2 y values for one x value, then we know that it's not a function. Now, this is the easiest thing. This is called a vertical line test. If we can draw a vertical line that intersects the relation more than once, then it means it's not a function. So if it fails a vertical line test, then it's not a function. If it passes a vertical line test, like it would up here, so here's an x value, and we could do the same thing for all the x values and see that there's only one y value for each x value. All right, to go into a little bit further detail, we can look at types of relations. So as far as we're concerned, we're looking at 4 different types of relations. We have a one-to-one relation. Now, when we look at these, the green is talking about y solutions, and the red is talking about x solutions. So in our first type, one-to-one, that's saying that for every x solution, there's only one y solution. Now, obviously, this is a function. We're happy with that. That should be a function. Only one y solution for each x solution and vice versa. Now, when we look at a many-to-one, so that means that there is only going to be one y value for each x value. But if we flip that around, the many-to-one means that there could be more than one x value for each y value, and that's okay. That's still a function. If we put in our vertical line, then it's going to pass. It's only going to have one y value for each x value. Now, when we flip this over, we get a one to many. So that means that there's only going to be one x value for each y value, but for each x value, there can be more than one y value. So that's a one to many. And in this case, it's going to fail that vertical line test. We've got two intercepts on that one vertical line, so this is not a function. And then finally, we've got many to many, and that means that if we put a vertical or a horizontal line, we'll see that there's going to be an intersection. So for each x value, there's multiple y values, and for each y value, there's multiple x values. So again, this is not a function. Now, you don't have to know these classifications really well, but it is nice to kind of break that down. Now, we know that one-to-one and many-to-one are functions, and one-to-many and many-to-many are not functions. Okay, so now we'll look at a couple of examples. So you'll see that I've pulled out my graphics calculator. At this stage, and well, you should probably be able to sketch these nice and easily, and we'll quickly talk about discrete and continuous. Sketching these is going to be something we continue to work on, where we can just use substitution or we can use our graphics calculator. I'll show you both. We'll do the first one by hand, and then the second we'll use our graphics calculator. Okay, so remember, discrete means there's only finite amount of values. So this 1, 2, 3, 4 is finite. There's just 4 values that we can sub in. And continuous means that there's going to be no gaps. Basically, it's an infinite number of ordered pairs or infinite coordinates. It's going to be a solid line. So when we look at A, and we've got y is equal to x squared, and our x values are nice and easy. We've got x is 1, 2, 3, 4, and it's discrete. It's only those values. We don't care about the values in between. If we sub the 1 in, we get 1 squared, and 1 squared gives us 1. If we sub in x equals 2, we get 2 squared, and that's 4. 3 squared is 9, and then 4 squared is 16. So obviously this is discrete. And then to sketch that, we don't want a solid line join in it. We just want to put in the points. Okay, so we've got 1, 1. We've got 2, 4. We've got 3, 9. And obviously my Cartesian plane was inadequate and we can't put that 4, 16 on. But you should get the picture there. So it's nice and easy to sketch. And it's pretty easy to say that's a discrete function. Now when we look at B, we've got y is equal to 2x plus 1. We've got here x is an element of a set of real numbers. Now, this set of real numbers means it can be anything between negative infinity and infinity. Not just whole numbers, but any number. For us, in this one, we're going to use our graphics calculator. So let's just enter this into x plus 1, and we're going to draw that. Now, if we want to, we can use the trace function, and we can get a couple of points from here. So using our graphics calculator, we've got x and we've got y. When we go down to -2, it is -3. So -2, -3. Let's put in 0. We know that that's going to be at 1. So there's 0, 1. And let's put in 2. And at 2, we're going to be up to 5. Now, because this one is continuous, we're able to look at all values, then we draw our line in between it. All right, so nice and easy. There's some examples of sketching and determining discrete and continuous. In these next examples, we just want to classify each as one-to-one, one-to-many, many-to-one, or many-to-many, and state whether each relation is a function or not. So if we look at our first one, let's use our calculator again. So we'll turn this one off. Remember to turn it off. We just select on it, so it won't graph again. Okay, so we put in our bracket. We've got x plus 3 bracket, x take 1 bracket, and x takes 6. All right, when we draw this one, it doesn't fit very well. So we're going to go view window, and we'll choose F3 for standard. And we'll look at how that sketches. We probably need to change our y values a little bit more. So let's change our y values to -30. up to 30. So I'll have a bit of a look at that. We could make the lower limit down to maybe -50. Okay, beautiful. Now, when we look at that, it's fairly obvious, I hope. So if we just sketch what we see there, now it's pretty important to maybe pull out the critical features, and we've talked about this before. The critical features will be the x-intercepts, y-intercepts, and so on. So if we go gsolve roots, which gives us the x-intercepts, we know we've got one at -3. We've got another one when we go across at 1. And then we've got another one when we go across at 6. And we can go gsolve y-intercept. We get 0.18. And then we can draw the rest of this through, just so it looks close to the same. Now the important thing here is we can see these vertical lines. There's only one y value for each x value, but when we flip it around the other way and we put in a horizontal line, there are more than one x values for each y value. So that means we're looking at a many-to-one relation, which would be a function. Okay, so that's nice and easy. Now, the second one, it's just a discrete set. We've got 3 coordinates to graph. So let's quickly put in those coordinates. We've got 1, 3. We've got 2 and 4. And then we've got 1 and 5. Now the giveaway here is vertical line. We've got a problem here. It's definitely not going to be a function because we've got 2 points that's sitting over the top. So 1 x value, 2 y values. So that means we've got a many-to-one relation, and we know that is not a function. Okay, so this classification takes time. The more you practice, the better you'll get at it. Test out your knowledge and see how you go. And if you have troubles, and you have to seek maybe some more help. But for now, hopefully that's enough to get you started with this. All right, the final thing in this lesson is domain and range. Domain is simply the possible x values for a graph, function, or relation. Now, sometimes this will be stated and sometimes this will be implied. So, for example, stated could be in the form of a set of ordered pairs. So we've got 1, 1, 2, 2, and 3, 4. So a domain, in this case, would simply just be x is an element of, and the values are simply discrete values. It could be 1, it could be 2, or it could be 3. So that's stated and discrete. The x values are 1, 2, and 3. Now, if we take something else like y is equal to x plus 3, where x is an element between 0 and 5, this is another stated. So it actually tells us straight away what the domain is. It's saying that for this particular graph, we're just going to look at graphing between 0 and 5 inclusive. So this is a stated domain. So this one's really nice and easy for us. We just have to say, well, our domain is x is an element of 0 to 5. Okay, so that's what we're looking at. It's either going to be stated or it's going to be implied. So implied's a little bit more challenging. If we don't have a stated domain and it's a type of function where we can see no issues, so let's have a look at, again, our y is equal to x plus 3. Let's say we're just looking at that. Now, what we have to think about is, for this x value, is there any x value that we can't sub into that? So is there any x value that if we put it in, we can't get an answer? And if the answer is no, they all work, then the implied domain in this scenario is that x could be anything. So x is an element of all real numbers. Now, the flip side of this is that if there is a scenario where x can't be certain values, so let's look at y is equal to square root of x plus 9. Now, because this is a square root, we should be able to determine that there's some values that just won't work here. So with a square root, if it's negative, then there's not going to be a real solution. If x is less than -9, then this is going to be no real solution. and that's going to break our scenario. So that tells us, with this implied domain, that x is an element of our smallest possible value is -9, because if we put in -9, we get 0, and that's okay. And our biggest possible value, obviously, is unlimited. We can go up to positive infinity. All right, so a stated domain is nice and easy. Implied domain is a little bit harder. We have to think about the problem and consider the values that we could possibly insert into that function or relation. Now, range is simply then the possible y values for the graph, relation, or function. So now we're looking at those limits to the y values. Now, generally, with range, we'll have to work it out ourselves. So most of these are implied, or at least we're trying to calculate range values. So all must be considered or calculated. All right. So a couple of simple examples here. We're just looking at the y values. So the first one, we'll look at y is equal to x plus 3, and we'll give it a set domain. X is an element of 0 through to 5. Now, we can use our graphics calculator to graph this out, and we will. I'll talk about it as well. So we'll turn this one off. We'll deselect it. We've got x plus 3, and we'll go comma. We can put in a square bracket, and we want to go between 0 and 5, and we can put in another square bracket, put that in, and we can sketch it. So we'll just view window, we'll change it back to standard. Look, there it is. So we can already see straight away that the domain, the x values only go between 0 and 5, so that follows what we want. With the y values, we want to look at what the smallest y value is and what the largest y value is. So the two ways we can do that is we can sub some values in, or we can look at the graph and work from there. So if we draw this graph that we've got up, I know when I sub in 0, I get an answer of 3. So this lower value is going to be 0, 3. And I know when I sub in 5, I get an answer of 8. So this upper value here is 5, 8. So there's our graph. We could also use trace to do that. So you can see there 0, 3. And when I sub in 5, I get 5, 8. So the smallest y value is 3. And the largest y value is 8. So that means my range is going to be y is an element. Now it's y is an element because we're looking at the y values. The smallest value is 3 inclusive, and our largest value is 8 inclusive. So there's our range, our limits in our y values. All right, sometimes it's a little bit more complex than that, but we'll look at a couple of examples now, and hopefully we'll see that pop up. So for each of these, we're looking at the domain and range and whether it's a function or not. So for each x value, and here's our problem here, we've got 2, 0, and 2, 3. So if we did graph that, we get 2 points above. So we know it's not a function, and our domain will just be the x values that are included. So we've got 1. We don't have to put 2 twice. So 1, 2, and 5. So you can't repeat values in sets. And with our range, we'll look at the y values. So y is an element. And our y values are, the smallest one is -1. And then we've got 0 and 3 and 4. So nice and easy. There's our domain. There's our range, not a function. The second one, we can see straight away that it is a function because it would pass that vertical line test. We can draw a vertical line at any point, and it's only going to intersect 1. So it's a many-to-one function. Now, our domain, because these arrows here, it continues on forever, which means we're going to have every possible x value included. So our domain is x is an element of all real numbers, and our range is a little bit different. So we know that can be any value up to positive infinity. That's where we're heading off to. But the lowest y value we can get is -2. So y is an element of -2 is our lowest value, and we're going up to positive infinity. And next one is a many-to-many. So as soon as we see that it's a many-to-many, then we know that it's not a function. And we can look at our domain, and we can see there's only a graph between -1 and 3 in x. So x is an element between -1 and 3 inclusive, and range y is an element, and our lower value is -2 and our upper value is 2. So y is an element between -2 and 2 inclusive. Now our final one's in set notation. So we're saying we've got a set of ordered pairs, and to calculate y we use for take x cubed. Now if we don't know what that looks like, we can use our graphics calculator again. So we'll turn this fella off. We'll put this one in. So we've got 4 take x cubed. And there's our graph. So we can draw this one in. Now as soon as we see this, we can see that it is a 1-to-1 relation, which makes it a function. There's only one y value for each x value, so that's good. Our domain, we can see that continues on. Now, we can see that there's no x value that exists, so we can't sub into that. There's nothing that's impossible there. We can choose a large number or a very negative number, and it still works. So in this case, x will be an element of all real numbers. With our range, we can see that that's continuing up to positive infinity, and this is continuing down to negative infinity. So the range will also be any possible value. So y is an element of all real numbers as well. Okay, so again, this is something that takes practice. We want to use our graphics calculator. We want to think. We want to go, is there any value we can't sub in? And we'll get better and better at this as we continue to do it over the next 2 years. Our final question is a little bit harder. We're looking to sketch the graph, state the domain and range using interval notation, but we're going to have to consider an implied domain, okay, because it doesn't tell us. So this first one, straight away, it's the perfect example for us because we already looked at one of these. We know that square roots are impossible when they become negative. So that means that anything less than 1, so x must be greater than or equal to 1 for this to work. If it's 0 or it's negative, then we get a negative number, and that's impossible. So we'll put this in, we'll graph it. We'll graph this, and we'll look at square root of x take 1. So we know that's our inverse parabola. We can see here, straight away, we can see the domain and range. It doesn't exist on the left-hand side, and it doesn't exist in the negative. So if we draw our little sketch here, then we go trace. Let's put in 1 because we know that's the smallest possible value. Our value here is 1, 0, and there's our graph from there, x and y. From there, it's pretty easy to say that, okay, my x values, 1's the smallest value, and it goes up to positive infinity. So our domain is x is an element from 1 through to positive infinity in a circle bracket because non-inclusive. And our range, we can see the smallest value is 0, so y is an element. 0 is the smallest value. And we're increasing here as well, so we're going off to positive infinity in the range as well. When we look at the second one, we can graph that as well. So x squared take away 4. Now the cool thing here is that they give us a stated domain. So even without graphing this, and we'll set that up, x and y, we know that our domain already, because it's stated, is that x is an element between 0 and 4. So we don't care about anything else. We just care about those y values that come from the x values between 0 and 4. Square bracket 0, comma 4. And close our square bracket, and we'll draw that, and we can see straight away that yep, it does stop, and we can trace, and we realize our smallest value is -4. So let's put that in, -4 here. we can find our x-intercept if we want to. So g solve root, and we get that's at 2, 0. Not important for domain and range, but important for sketching. And if we trace, and the biggest x value is 4, and we get 12 up here, so 4, 12. And there we go, there's our graph. We use the colored dots to end it. There's no arrow to continue. And our range is simply y as an element. The smallest value is -4, and the largest value is 12. Now these are both inclusive because the x values were inclusive. So there's our domain and range. Okay, so that concludes the lesson. I know there's a lot there, but it is a review. You'll need to make sure you work through the set in the next tab, and that will give you enough practice with all of this. Okay, thank you.